We'll now have a look at the domain name system, or DNS. The purpose of the domain name system is to map human-readable names, such as www.gatech.edu, to IP addresses, such as 130.207.160.173. A name such as this is human-readable and much easier to remember and type than an IP address. But in fact, the IP address is what's needed to send traffic to the intended destination, so we need a lookup mechanism that takes a human-readable name and maps it to an IP address. The system that does this is the domain name system, or the DNS. The system roughly works as follows. A client might want to look up a domain name, such as www.gatech.edu. A networked application's source code might do so by invoking a function such as getHostByName, which takes as an argument a domain name and returns an IP address. The client typically has what's called a stub resolver, and that stub resolver takes that name and issues a query. The stub resolver might have cached the answer, or the IP address corresponding to this name, but if not, the query is sent to what's called a local DNS resolver. Your local DNS resolver is typically configured automatically when your host is assigned an IP address using a protocol called the Domain Host Configuration Protocol, or DHCP. In your host configuration, such as this one, you can see that this local host has two local DNS resolvers. Typically, a client will try the first DNS resolver, and if it doesn't receive a response within a pre-configured timeout, it will try sending the same query to the second local DNS resolver as a backup. This query is typically issued recursively, meaning that the client does not want intermediate referrals sent back to it. It only wants to hear when it's received the final answer. The local resolver, on the other hand, will perform iterative queries. It might have the answer to this particular query in the cache, in which case it would simply reply with the answer. But let's suppose for the moment that nothing is cached. Each fully qualified domain name is presumed to end with a dot, indicating the root of the DNS hierarchy. Now, the IP addresses for the root servers, or those that are authoritative for the root, may already be configured in the local DNS resolver. In this case, the resolver may be able to query for the authoritative server for .edu at, say, a.rootservers.net. This would be an A record query, but the answer might return with what's called an NS record, which is a referral. In this case, the answer might be a referral to the EDU servers. Now the local resolver issues the same query to the EDU servers and receives a referral to the authoritative servers for gatech.edu. Finally, the local resolver might query the authoritative name server for gatech.edu and actually receive an A record indicating the actual IP address that corresponds to that name. Now, this process of referrals, as you can see, can be rather slow. A particular DNS query might thus require round trips to multiple servers that are authoritative for different parts of the hierarchy. The blue server is authoritative for the root, the purple server is authoritative for .edu, and the red server is authoritative for gatech.edu. Now, supposing we wanted to save the extra time and trouble of these round trip times, this local resolver would typically have a cache that stores the NS records for each level of the hierarchy, as well as the A records. And each of these answers would be stored or cached for a particular amount of time. Each one of these replies has what's called a time to live, or a TTL, that indicates how long each of these answers can be saved before they need to be looked up again. Caching allows for quick responses from the local DNS resolver, especially for repeated mappings. For example, since everyone is probably looking up domain names such as google.com, it's much faster to keep the answer in cache. So given multiple clients trying to resolve the same domain name, the answers can all be resolved in a local cache. Some queries can reuse parts of this lookup. For example, it's unlikely that the authoritative name server for the root is going to change very often, so that answer might be kept or cached for a much longer period of time. A typical time might be hours or days, or even weeks. The mapping for a local name, such as www.gatech.edu, on the other hand, might change more frequently, and thus these local TTLs might need to be smaller. Now, the most common type of DNS record is what's called an A record, which maps an IP address to a domain name. But there are other important record types as well. A records map names to IP addresses, as we've seen. We've also seen what's called an NS, or a name server record, which maps a domain name to the authoritative name server for that domain. So we saw a bunch of NS records in the form of referrals, whereby if we ask the root for a mapping of gotek.edu to an IP address, it doesn't specifically know the answer, but it can issue a name server reply, or an NS record, referring the resolver to a different name server that could be responsible for that part of the domain name space. This allows the domain name system to be implemented as a hierarchy. Another important DNS record type is an MX record, which shows the mail server for a particular domain. Occasionally, one name actually is just an alias for another name. For example, www.gotek.edu actually has a slightly different real name. The CNAME is basically a pointer from an alias to another domain name that needs to be looked up. The PTR is another record that we'll look at, and this maps IP addresses to domain names. For example, if you wanted to know the name for a particular IP address, you need to issue a PTR query. This is sometimes called a reverse lookup. Finally, a quad A record maps a domain name to an IPv6 address. Let's take a look at a couple of different examples of domain name lookups using a command line utility called dig. As a quick quiz, which DNS record is used for a referral? Is it the MX record, the A record, the quad A record, the NS record, or the PTR? The NS record indicates the authoritative name server for a particular portion of the domain namespace, and an NS record reply is often referred to as a referral. MX records indicate mail servers, A records are IP addresses for the domain name, quad A are for IPv6 addresses, and a PTR is a name corresponding to an IP address being queried. Here's an example of a lookup for an A record for gotek.edu. You can try this at your own command line by typing, for example, dig www.gotek.edu. Now there are some interesting things to note in this trace. Here is our query, and you can see that this is an A record query. Here's our answer. You can see that the answer actually has a CNAME in it, which basically says, well, you asked for gotek.edu, but in fact, what you really want to ask for is tlweb.gtm.gotek.edu. So then we issue an A record query for that name, and we ultimately get the IP address. These numbers here indicate the time to live, or the amount of time in seconds that the entry can be stored in the cache. Here's another example of a DNS lookup for nytimes.com. The interesting thing to note here is that in response to the A record query, we see two IP addresses. This is typically performed when a service wants to perform load balancing. So the client could use either one of these. It might prefer the first one, but if we issued the same query again, we might actually get these IP addresses in a different order. Now again here, you can see the TTL value, which indicates how long these A records can be stored in cache. In a subsequent example, we'll look at other query types that have much longer TTL values. Here's an example of a query for the NS record of gotek.edu. You can see this output by typing dig ns gotek.edu. You can see here in the question section, now instead of an A record query, we have an NS record query, and our answer is a bunch of NS records that are DNS1, 2, and 3.gotek.edu, any of which could answer authoritatively for subdomains of gotek.edu. You can see that in addition to the answer, which return the name servers, we also need the IP addresses of those name servers, which is returned in the additional section of the answer. You can see here that we received not only A records for each domain name, but also quad A, or IPv6 addresses corresponding to each authoritative name server. Here's an example of a query for an MX record, or the mail server corresponding to gotek.edu. Now here again you can see the question as the MX record, and you can see the answer, which returns two mail servers, as well as the additional section, which returns an A record indicating the IP address corresponding to the mail server that was returned in the MX record. In addition to the TTL, we also have some metrics that indicate priorities that it would allow a system administrator to configure a primary and a backup mail server. In this case, the mail servers just happen to have the same priority level. Let's put everything together now by looking at a trace of an entire lookup. Now, in the examples before, we didn't get to see the full lookup hierarchy because we issued a recursive query. But let's suppose that we wanted to see every step of the DNS lookup process. You can do this by using the trace option in Dig. Here you can see exactly what we saw before, which is the local resolver, in this case issuing a query to a local resolver and receiving a referral to an authoritative server for dot, which could be any of the following. That query elicits an answer for the .edu servers, which subsequently issues a referral to the servers that are authoritative for Gotek, which ultimately reply with the appropriate A records as well as the authoritative name servers for Gotek.edu. A final interesting example explores how to map an IP address back to a name. In this case, we're ultimately looking for a PTR record, which is the name corresponding to this IP address. But first, what happens is we receive a special referral. When we ask the root servers about this particular IP address, instead of being referred to a particular .com or .edu domain, we're referred to a special top-level domain called inattr.arpa, which maintains referrals to authoritative servers that are maintained by the respective internet routing registries, such as ARIN, RIPE, APNIC, and so forth. So here we see a referral to inattr.arpa. Subsequently, we see a referral to 130.inattr.arpa, corresponding to the first octet of the IP address. Next, when we ask ARIN about 130.inattr.arpa, we receive another referral, which is to 207.130.inattr.arpa, and because 130.207 is allocated to Gotek.edu, ARIN knows that the appropriate referral for this part of the address space is to DNS123.gotek.edu. Next, we issue a query for the next part of the octet, 7.207.130.inattr.arpa, corresponding to the first three octets. And now we actually get the PTR because DNS3.gotek.edu knows the reverse mapping between 130.207.7.36 and the name for that IP address. So you can see that the PTR records, or those that map IP addresses to names, are resolved through a special hierarchy through inattr.arpa at the root, followed by a walk through the regional registries and ultimately to the domains, such as Gotek, that are responsible for particular regions of the IP address space. As a quick quiz, suppose we wanted to look up the IP address 130.207.97.11. What is the corresponding inattr.arpa domain name? Is it 130.207.97.11? Is it 130.207.97.111.inattr.arpa? Is it inattr.arpa.130.207.97.11? Or is it 11.97.207.130.inattr.arpa? The corresponding domain name for the PTR lookup for this IP address is the record corresponding to 11.97.207.130.inattr.arpa. Notice that the reversal of the octets in this name corresponds to a strict traversal of the hierarchy from the highest levels of the hierarchy at inattr.arpa to the lower levels as the IP address moves from higher to lower parts of the hierarchy.